Assume you're a kid and you have some blocks and a friend who also has some blocks. It would be nice to quantify how many blocks you and your friend have, so you could invent some number system to do this. If you did this, you might come up with what are called the natural numbers. These are the positive whole numbers, i.e. 1, 2, 3, ... You might also want to do stuff to the blocks, like give blocks to your friend or take blocks from your friend, so you make up addition and subtraction. Also, maybe after you come up with addition you really like it, so you keep adding the same number multiple times and call this multiplication. However, at this point you realize there's some problems. What if your friend has 3 blocks and you want to take away all of them? This is where it would be a good idea to invent the number 0. But what if he has 3 blocks and you want to take away 5 blocks? Now it would be a good idea to invent negative numbers. Let's also assume you're not too concerned with what negative numbers mean, you just want to subtract with impunity. So now you have positive whole numbers 0 and negative whole numbers, but you're not quite done. You still have to define how 0 and negative numbers interact with positive whole numbers and each other. This is where you come up with rules like any number multiplied by 0 is 0, and 2 negative numbers multiplied by each other give a positive number. Once you have figured out these rules, you have the integers. Next, you might notice subtraction is like the opposite of addition, so maybe multiplication should also have an opposite. This is where you invent division. However, like subtraction, it doesn't work perfectly. For example, if you try to divide 5 by 2, you get an annoying remainder. So like before, you make up some new numbers to make things work and call these numbers fractions. Extending the rules of addition, subtraction, multiplication, and division to fractions requires some work. One of the key issues is the same fraction can be represented in multiple ways. For example, a half is the same as 2 and 4. If you figure out how to extend the rules, you get the rational numbers. Then you get a system of numbers where you can divide things as long as you don't divide by 0 and things work. Since you are dealing with blocks, you might become interested in geometry. When you do this, you might encounter numbers like the square root of 2 and pi. At this point, you realize there are things that should be numbers but are not rational numbers. This is also the point where going to the next level of numbers gets confusing. You could add root 2 to the rationals and create rules to extend addition, subtraction, multiplication, and division. Then you would have what is called q root 2. However, q root 2 does not contain root 3, so you might want to add that, but root 5 won't be in there, and so on and so forth. A different approach is to think in terms of sequences of numbers. Let's take the sequence 1, a half, a third, a quarter, ... We know in some sense that terms approach 0. The first step is to formalize this with the notions of limits and convergence. Once we define the concept of a convergent sequence, we define the notion of a Cauchy sequence, which is like a convergent sequence, but instead of saying the terms in the sequence become something, we say they become close together. Then the real numbers are the rational numbers, but there are new numbers in there, so all Cauchy sequences converge. This will mean numbers like root 2, pi, and e are in there. The reason for this is we can construct Cauchy sequences that only contain rational numbers that become these numbers when all Cauchy sequences converge. It is often said that the real numbers are what you get when you fill in the gaps in the rational numbers. If this sounds confusing, it is because it is. Part of the reason for this is when you start dealing with infinite sets, a lot of the intuition that works with finite sets no longer works. Once you have the real numbers, things are pretty good. However, maybe you realize the equation x squared plus 1 has no solution and get annoyed. So you make up a solution for it and call it I for imaginary. Extending addition and subtraction are easy. You just keep the real and imaginary parts separate. Multiplication and division are not too bad either. You do what comes naturally and keep in mind I times I equals minus 1. You do this and you get the complex numbers. You might be wondering, well, now we have a solution for the equation x squared plus 1 equals 0 by inventing complex numbers. But maybe now there are a whole bunch of new polynomial equations that don't have solutions and we need to invent new numbers to solve those, and the process never ends. Fortunately, there's a result called the fundamental theorem of algebra, which tells us this does not occur. Once we get to C, every non-constant polynomial has a root. By non-constant, we mean equations like 3 equals 0 still have no solution, but for now that probably doesn't bother us. One of the interesting things about the complex numbers is they give a way to give an algebraic structure to a two-dimensional vector space. A mathematician by the name of Hilbert wanted to do a similar thing in 3 dimensions. He couldn't do it in 3 dimensions, but he was able to do it in 4 dimensions and created the Quaternions. The Quaternions are like the complex numbers, but instead of a plus bi, you have a plus bi plus cj plus dk. To define multiplication, you let I times I equal -1, j times j equal -1, k times k equal -1, and I times j times k equal to -1. Unlike the number systems we have seen so far, Quaternions don't have the property a times b equals b times a, which is called commutativity. For example, I times j equals k, but j times I equals negative k. There are also octonions, which are in 8 dimensions and stranger. All the number systems we have dealt with so far have been infinite. Another option is to keep things finite. One way to do this is through the concept of a finite field. We can create a simple example of a finite field by starting with a prime number. Let's choose 5. The basic idea is to call all numbers equivalent if they have the same remainder when divided by 5. For example, 8 divided by 5 leaves a remainder of 3. So in this field, 8 and 3 mean the same thing. Since there are only 5 possible remainders, namely 0, 1, 2, 3, and 4, we can choose these to make the only elements in our field and use remainders to ensure we only deal with these numbers. To multiply two numbers in this field, we do things as usual and take remainders. For example, if we do 2 times 8, we get 4. Now when we take remainders, we get 3. So in our field, 2 times 4 is equivalent to 3. We also have the usual properties. 0 times anything is 0, and 1 times anything is itself. Instead of considering division directly, we start with the notion of inversion. Let's say we have a non-zero number in our field, for example 2. If we multiply 2 by 3, we get 6, which becomes 1 after taking remainders. Because 2 times 3 gives 1 in our field, 3 is called the inverse of 2. So how do we define division in our field? Well, the idea of division is to undo multiplication. So we can define dividing a number by a as multiplying the number by the inverse of a. So in our field, dividing by 2 means the same thing as multiplying by 3. As a side note, addition and subtraction also work in a similar way. It turns out as long as we do this construction with a prime, every non-zero number will have an inverse, and thus we can define division. So we can work with other primes such as 2, 3, 7, 11, 13, or even 1,000,000,007. You may be wondering why restrict ourselves to primes. Why not do the same thing with other numbers like 4? The problem with 4 is we can't define dividing by 2. Let's go through the options. 2 times 0 gives 0, 2 times 1 gives 2, 2 times 2 gives 4, which is the same as 0, and 2 times 3 gives 6, which is the same as 2. Now, if division is not that important to you, you can do what we did above. However, let's say you wanted 4 elements and division. It turns out there is a way to do this. The key is to start with the field with only 2 elements, i.e. 0 and 1, and we consider remainders dividing by 2. Now we do a similar thing to what we did when we created I, because the equation x squared plus 1 has no real solution. In this case, consider the polynomial x squared plus x plus 1. If you put in 0, you get 1. If you put in 1, you get 3, which becomes 1 when we take remainders. So in this field, this polynomial has no root. So you invent a new number, call it a, and say a has the property that a squared plus a plus 1 equals 0 in this field. Now you get 2 new elements in your field. These are a and 1 plus a. With some work, you can figure out how addition and multiplication tables work, and you have a field with 4 elements. In conclusion, mathematicians like to invent things. Sometimes the things they invent are numbers, and sometimes these numbers have interesting properties that previous numbers they invented did not have. If you are interested in what are real numbers, you could study real analysis. If you are interested in complex numbers and the proof of the fundamental theorem of algebra, you could study complex analysis. If you are interested in finite fields, you could study abstract algebra.